It's about clustering of resources. So for example, if I push a large file to S3 or Google Cloud Storage, that file could potentially be stored across hundreds of separate disks. It's distributed, it's redundant, so you have chunks of that file living in many different places, which is why in big data applications you can push data very rapidly because you have all those disks working together. Same thing, you have these massive clusters of machines, and instead of thinking of services living on a single machine, you want to think about services running across a whole bunch of machines at the same time and communicating with each other. And generally when we talk about serverless services in the cloud, we're talking about things that run in clusters across large numbers of assets. So for instance, if you're using AWS Lambda, that Lambda can fire maybe initially from one machine, but if you hit it with a bunch of traffic, it will spin up on a whole bunch of machines at once wherever AWS happens to have resources at the time, and load balancers will determine where those requests are going. So in terms of containers, you want to think about having a cluster of these assets and then spinning up a bunch of different services that live in different places. And then instead of using kernel message passing, we now use networking, which allows us to communicate with a much wider world. So we're not just isolated to that one machine. We can communicate within our cluster, or maybe we can communicate with other data centers, or our services can communicate with the general web. And then instead of Linux as our operating system, of course, we still have Linux running on these individual machines, but at scale, Kubernetes can be thought of as an operating system for clusters. So managing hundreds or thousands of different services running across a bunch of different machines. Just wait a second here. Okay, this is, some of this was driven by my own experiences with Python portability. So I mentioned some of this. These are issues I've run into with trying to run code on a new machine or move something that I've developed on my laptop to a virtual machine, for example. So incorrect package versions, dependency conflicts. These first two are fairly easily resolved with virtualenv, but if you go down the list, you run into things that are a little harder to deal with. So host text encoding issues. The OS will have a different setting for UTF-8, and that will cause my app to fail. That's happened more than once. C compiler compatibility. So at one point, back in the Stone Ages, I was on Windows, and a new version of Python came out, and they compiled it on a different compiler, and then when I tried to pull things from pip, from PyPy, the correct wheels versions weren't there that were compatible with that compiler, and so I wasn't able to install things easily. Incorrect TLS library versions caused incompatibilities for me. And it's not that containers magically resolve all of these issues. In the container itself, you still have to install your code, but once you've done that, it gives you you install once and run anywhere. So it gives you a portable executable, so you don't have to do that same thing again and again. I can just take my app that I've run locally, I can deploy it to the cloud. Yes.
So but Python does compile differently for different OS,
yes.
Like Windows, Linux, Mac. It'll compile differently, so you can't just take that binary and put it on anything.
Right. So that's where Docker comes in. So there are Windows kernel containers, but in general, when we talk about Docker, we're talking about containers that run on top of the Linux kernel. And so when you install Docker machine, it comes with all that stuff you need to run. Now, one point you might be getting at is there are different architectures, and that is a good point. So I'm kind of assuming in general that you have an Intel machine. It could be a Mac, which is running Mac OS. It could be Windows, or it could be an AWS virtual machine. And that container will be able to run on any of those architectures because the Docker machine will provide the kernel that you need, essentially. Does that make sense? Or?
But I thought Docker didn't provide the kernel that it ran on. You're still running on that machine or that OS.
Right. So
kernel, like the container, has all of the pieces together.
Right.
But Python, when it goes from your raw Python code,
yes.
it compiles down.
Yes.
Often needs to be compiled, at least if not on the same type of machine, on like the same either Linux, Windows, or Mac.
Right, and so what happens is if I run Docker machine on my Mac, it actually includes a copy of the Linux kernel with it. So there's a little extra weight that you're carrying around there. But the nice thing there, so on Linux, it just uses the native Linux kernel, but on my Mac, it uses a virtualized kernel instead. So I don't have to recompile anything for that reason.
But you do want to make sure that your containers, like whatever virtual machine you're running your container on, is going to be equivalent.
Yes. The container is whatever operating system, right? So your container can be a Linux inside of the container. Right. So then that container, you take it to a Mac instead. Right. It's the same container. It's the underlying Docker infrastructure will say, oh, okay, this is a Linux kernel inside of this. We'll spin up and run, and it works the same way across Windows, Linux, Mac.
Exactly. So once I've compiled my Python code, it will run on any of those architectures so long as I have Intel and so long as I have a Docker machine installed. That's the basic idea. So beyond that, I mean, there are some complications, like I have to provide some configuration potentially. I may need to provide it some disk space and things like this. But the app should run as is. So I'm actually going to do a real quick demonstration. I'll keep an eye on the time here. So two things I want to demonstrate. Let's suppose that we want to run the latest version of Python that hasn't been released yet. So Python 3.7 is in its second beta now. And of course, installing this yourself would be a huge pain, and then you'd have to install each upgrade as it came out. And so what I'm going to do is grab the Python public container for that beta, and then I can just spin that up immediately. So let's see. Let me just show you where this is coming from. Okay, so these are pre-built containers that have Python installed, and these tags indicate different flavors of that container. So I can, for instance, run a Python 3.6.5 container. Stretch refers to the release of Debian that this is built on. I'm going to run, I'll show you here. Let's see. What's that? Is it?
I'll make it big.
Oh, make it big, yes. Anyone?
Command plus.
Command plus here too. Okay, cool. How's that?
One more.
Is that good? Yeah. Okay, cool. Okay, so these details are in my slides, so don't worry about copying them down or anything like that. But basically, what I'm doing here, so I'm doing a Docker run. I'm going to run a command inside of a container. This rm means to throw it away when you're done, basically. Don't keep it around. And then I've got this Python container and release candidate on Alpine Linux. So it's going to grab the latest version of Python that's in beta right now. And let's try that. Okay, so I see what I have here is Python 3.7.0, second beta. And so if, for instance, I'm a developer and I'm excited about a new feature on the very latest release of Python, I can grab this container and start developing before it even releases. And then I can start building my code into these containers so that when the official Python 3.7 release comes out, I then have an artifact that can be deployed. So I can deploy it on AWS Fargate or on Google Container Engine, for example, or I can give it to another developer for them to run and test. And so, of course, this is not a particularly interesting thing to do, but you might, for instance, experiment with data classes or some of the other new features that are coming out in Python 3.7. Who here has heard of PyPy? Of course, that means two different things. Okay, so what is PyPy exactly?
It's a package distribution.
Okay, so there's that PyPy. What's the other PyPy? Yes, it's a faster version of Python. So what's the problem with PyPy? There are two issues. First of all, it's kind of a pain to install and manage, have extra code to manage. And second, it's not 100% compatible. And so you'd like an easy way to manage it, and you'd like an easy way to just test quickly an existing app to see if everything runs. So say you have a test suite, you just like to try it in PyPy, make sure all the tests run, and then maybe do some performance testing to see if it's worth deploying your app with PyPy. So what I'm going to do this time is pull the PyPy container, and again, I won't do anything particularly interesting, but we'll be running inside this container with the just-in-time compiler for Python. So these commands, of course, I had up earlier, which so I can pull them up so quickly. And so I'm pulling up the PyPy container, the default one, and I'm going to run PyPy 3, which means Python 3 with this just-in-time compiler running. Okay, and so here I am. It tells me that I have 3.5.3, PyPy 5.10.1, and then I'll do for just something really boring. Okay, and there it is. That doesn't give a compelling example of the performance, I suppose, but the idea is that I can quickly grab these different versions of Python. I can be on the bleeding edge if I want to, and in some ways this can supplement your virtual envs. Once you get in the habit of developing in containers, you may choose just not to deal with virtual envs and to just have different containers around that have pre-installed sets of options. And in fact, that's what I'm going to do in just a moment. I've got Airflow itself installed in a container, and I'll spin up 4 separate services off of that same container. Okay. Yes?
With the, so I noticed you have PyCharm installed, and with the different Docker environments for different versions of Python, are you able to tie your PyCharm into, like, for the interactive debugging?
That can be a bit of a pain point, and that brings up a valid point. What I generally try to do is line up and that's where I do use virtual envs sometime. And so I do have Airflow still installed locally so that mostly it's compatible and I can debug that way.
I saw an advertisement.
Yeah.
I didn't click on it. So
Yeah.
supposedly PyCharm does have the ability to reach into containers to do debugging.
Okay.
It does, and you can use it off your composed environment as well.
Oh, that's fantastic. Okay, so you're well ahead of me on this stuff.
And
Nice. Yeah. I mean, certainly you can map your code into a container just by mounting it as a volume and then run it dynamically that way. I should talk to you guys about this afterward just to hear more about the details. So, okay, and that's okay. So now I'm going to talk about data pipelines. So I'm going to get into the world of data engineering a bit. And data pipelines are by no means a new idea. This goes back to the concept of extract, transform, load, which I had not heard before I worked in the tech industry. But it basically means that we have a bunch of different databases, and we need to move data around, and we need to process it somehow. So the typical scenario where I work at Overstock is that we have a transactional database that needs to process thousands of transactions per second. So it has very low latency. It can process massive numbers of transactions asynchronously, but it's not great for analytics. Like, you don't want to hit your production Oracle database with a huge query to determine what your sales for the day have been so far, because you'll slow down the entire website, and it actually won't run very fast. Oracle is simply, that version of Oracle is not designed to do that. And so we want to suck data out of Oracle, and we want to move it over to another database, or maybe a big data system, where we can analyze it, and we probably want to join it with some other data. So in Oracle, we may just have transaction IDs in one table with some of those transaction details, and my business analysts want to see the details of those transactions, and so maybe I'll join that table with some sales line information, and then join the product IDs with the actual product names, and so on and so forth. And so that's all ETL. And then in this new era, we also care about machine learning, and we want to think of that as part of our data pipeline. So once an ETL process completes that sucks up a bunch of raw log data and then pushes it into my Hadoop cluster, I want to kick off maybe a Spark job that will analyze that data, and then it will spit out some output that then informs what the website services do the next day. And then in addition, in the last 10 years or so, of course, ETL has always been about these heterogeneous environments, managing a number of different databases and moving data between them. But now we need to deal with APIs. So maybe I want to pull data from the Google AdWords API. And maybe I want to move it to the cloud somehow. So maybe I want it to go to AWS or GCP, or maybe both. Increasingly, companies are multi-cloud because different clouds have different key strengths. Google is really great for containers and Kubernetes, and AWS is very solid and mature in other areas. In fact, for like Fargate, for instance, it's really phenomenal for containers as well. It's stronger for partnerships. So anyway, I need to move the data between all these different systems, and you often end up with something like this. You end up with these huge messes of cron jobs, and then if I drill into the individual Python files, I might try to define some complex dependencies and jobs within that Python file, but then it becomes very difficult to visualize what that Python file is doing. So when my code gets deep enough and complex enough, I really need to visualize it somehow to get a better grasp of what's going on. That's just how humans tend to work. We can see connections visually that are much harder for us to see in code in a very easy fashion. So we want to get away from this, and actually there are a number of tools around that let us do that. Oh, I should talk about DAGs first. So what is a directed acyclic graph? Oh, this is not coming through for some reason. Okay. The idea is that I have a number of tasks that I want to run, and I have some arrows that link these tasks together. And so each task needs to wait for its upstream dependencies to run. So for example, this run after loop might be some kind of join that relies on data from 3 tables, and so I need to run these 3 tasks before this can run. And so I can try to do something like that in Python, but again, it gets very complicated and hard to visualize, and so ideally my ETL or data pipeline system will support that. let's make a list of modern workflow management needs for data pipelines. So first of all, DAG support, and that's both being able to encode DAGs and visualize them ideally. I want robust version control, so I want to keep track of the history of my data pipelines. My assumption is that my data pipelines are going to evolve, and I want to be able to roll back if I have to. I want to be able to go back in history and see what was happening 6 months ago if I need to look back at data and there was a problem with that data. I want to be, let's say, on-prem native plus cloud native. So in other words, I should be able to connect to my IBM DB2 database to do things. I want to connect to Hadoop. I also want to be able to connect to Databricks or to DataPros and big data systems in the cloud. BigQuery, Redshift, Snowflake, you name it. There are all kinds of different things that I might want to talk to. And I want this to be extensible. So I really don't want to wait for a vendor to write a new extension so I can connect to a database that I'm spinning up on the cloud. I'd like to be able to write the code myself, maybe some API access call code that runs a job on that system. And also ideally, I'd like my system to be aware of history and time intervals. So to be efficient, I should probably process data in chunks. I really don't want to rebuild all history every night when I run my ETL jobs. I just want to process the new chunks that have shown up that evening or maybe in the last hour. And also, if I make a change to my data, then I'd like to rebuild the data going back over time. And maybe I can set a specific time range and say, rebuild just this one table, this one task, over the last 365 days. And I want to keep history of everything that's happened in my system. I'd like it to be scalable. So inherently, I want it to be able to run in a cluster infrastructure and get very large as I add massive numbers of tasks. And I'd like it to be able to notify me, and I'd like other visualization capabilities. So I want to be able to visualize which tasks have run and which tasks have failed easily. Okay, so here are a couple of workflow managers, and of course you know where I'm going with this. So if you've used Control-M, it's workmanlike. It can get the job done, but it's pretty old and creaky, and it tends to be used with legacy databases. And while it is somewhat extensible, it's kind of a code management nightmare to make it do everything that you want. And so we're going to eliminate that one from the list for now. Uzi and Azkaban. So the problem with these two is that they're domain specific, and I don't want domain specific. I mean, yeah, you can get Uzi to do all kinds of stuff, but that's not what it's designed for. It's designed to work on Hadoop. It's designed to work with the Yarn scheduler. And making it do other stuff is just not a lot of fun. And Azkaban, same basic idea. Airflow and Luigi. So Luigi is more like a build system for data pipelines. It's not really designed to keep track of task history. And the other issue is that open source in general is a popularity contest. That's why we're all using Linux right now and not FreeBSD, because Linux won that contest quite a while ago. And at least from the stats I've seen, Airflow seems to be winning that contest. And so that's what we're going to focus on. And that's what we've been using recently. This project was started by, I think it's Maxime Bauhiman, but I'm not.
It's kind of a fascinating deal.
Oh, go ahead.
Yeah, so you're saying it's a open source is a popularity.
I think so, yeah. So you kind of have to figure out which horse to hitch your wagon to, I suppose, because some open source projects will languish and die, or at least not expand very quickly. And ideally, you're on a project that has a lot of commits coming in, so that you'll have a lot of capabilities without having to write huge amounts of code yourself. So,
are you frustrated?
Not necessarily. I've written code for this project, but I wouldn't say I'm frustrated.
I mean, with just in general, with like you feel like the best horse isn't winning.
Oh, okay.
Yeah, with the popularity contest.
Yeah, I guess it's just one of those social realities that you deal with. Sometimes the best business doesn't win, and sometimes the best open source project doesn't win. And so you try to pick one you really want to support and contribute to. So, yeah. Okay, so this project was open sourced in 2015. Airbnb was using it internally before that. It's not clear to me how long they were, but it was meant to solve these problems: cloud native integration, extensibility, and so on. And so it's now an Apache incubator project, and I think their goal is to graduate out of incubator status and to become a top-tier project, maybe on the next release, which is in process now. And here's the address for the Git repo. You can take a look there, kind of see what's going on and see what capabilities are being added, and I'll talk about some of those. So I'm going to go through some of the things on this list. So DAG support and version control. So the concept in Airflow is configuration as code. And what that means is we just write Python files to define these data pipelines. And we're defining them as Python objects, which I'll show you in just a moment. DAG visualization to aid development. So once I write my file, Airflow starts scanning it immediately. It can take a minute or two, but eventually I'll get a visualization in the web interface. And so I can see if the arrows point the way they're supposed to be pointing, because that's important. And it's easier for me to see that than to try to read it in my code often. Okay, as far as extensibility, it's all Python. And Joe is fond of saying that Python is the second best language at everything. And that makes it really great for a big, complicated system like this. There are just tons of Python API libraries and clients, for instance. And so I can use Python to connect to all kinds of different different APIs without doing a whole lot of work. It's open source. And so at Overstock, we have made some changes to the core. We've added a couple of modules to connect to things that were not supported before. It's modular, and I'll talk about that a bit more in a moment. And it plays nice with Kubernetes and containers, which I'll show you. And it also, there's a new feature coming out in the next release called we'll see if it makes the next release, but the Kubernetes operator, which will let you easily control any job running on a Kubernetes cluster. Right now, you can do that to some extent by writing your own code, but this will make it substantially easier. So that makes it very easy to scale all kinds of different jobs on Airflow. So inherent to the design of Airflow is that it does keep track of history in a database, and it has the notion of a time interval. You put the time intervals that you want in your DAG definition files, and then you can do things like backfill. So I define a new data pipeline, and I say, I want this data, I want to process it once a day. I want you to go back in time and do this for the last year, and it will start, and it will work through that process. And then so scalability, Celery, someone mentioned Celery earlier. Celery is a cluster worker manager, and this is how I'm going to show you Airflow tonight. There are other executors, but Celery is the one I'm focused on, and that allows you to have a number of different workers in different places. First of all, the scale, and second, you can have a heterogeneous environment. So I can have, say I have a GPU machine living somewhere, I can put a Celery worker there, then I can send particular tasks just to that GPU machine, and then I could have another Celery worker that lived in the cloud and communicated with AWS only. And then Kubernetes operator that I mentioned. Notifications, so you can set it up to do email alerts when things fail. And there's a nice web interface for monitoring everything about your tasks, and also actually for, to some degree, controlling tasks. Okay, so the core architecture, let's see, when do I want to start this demo? So I'm going to start the demo now. It will take just a second for some of this stuff to work. And so I am doing this with Docker Compose, and if you're not familiar with Docker Compose, the basic idea is that Docker machine that you install on your laptop or wherever has the capability to create virtual networks, to create a number of containers and wire them together. But doing that with Docker machine is a huge pain. Like, you really don't want to do much of that. You'll pull your hair out. And so I forget which company it was, but a company came up with a solution, which is a Python wrapper around Docker machine that automates all of that for you. And eventually that turned into Docker Compose. And so let me just show you this real quick. Okay, so what is a compose file? Well, basically a compose file specifies a number of containers that are going to spin up, and it will run services inside of these containers and will expose ports for those containers to communicate with each other and to communicate with the outside world. And so in this case, I'm doing this with the Celery executor, which is way overkill for a laptop like this. You should probably use the local executor, which is in the notes at the end, if you're just messing around with Airflow or doing some experimental development. But this way you'll kind of get to see how this architecture works. And so at the top, Redis is a communication bus, in this case for Celery. It allows Celery to send out jobs, basically, and then the Celery workers will pick those up. Postgres is my backend database that stores all of my task history. And then I have a web server, which connects to the database and sees what's going on, and also it can update the database. So if I tell the web server to kick off a task, what it does is switch the status, or rather a DAG, it switches the status of that DAG to running, and then the executor will pick up that information and start executing it. Oops. Okay, Flower is a monitor for Celery, and so it looks at the Celery message bus and sees what's running. And then the scheduler down here scans my DAG files, and everything in Airflow is based on dependency, even time. Time is just another dependency for Airflow. It checks a DAG instance, and it says, is the time condition for this DAG instance satisfied? If it is, then it turns that DAG instance on. And then it starts drilling down and looking at the task instances. So if the DAG, the directed acyclic graph, is running, it checks each task to see if its dependencies have been satisfied. And if they have been satisfied, then that task is flipped to queued, where it will get picked up. And if not, then it doesn't do anything. Then I have my worker down here, and the way it's configured, it's a Celery worker. And so it will start up, and it will start 16 threads inside. And then each of those threads will check in with my Redis cache to try to pick up jobs to run. Okay, so let's start this. And if you do this, by the way, in all its glory, make sure to adjust the memory on your virtual machine, or it will crash, as I discovered Monday morning, and wasted a huge amount of time on because I forgot that this is a Mac, and so the memory is isolated in a virtual machine instead of shared, so I didn't get all 16 gigabytes. Okay, so this was way more painful than it should have been. I guess that's just life doing software. Okay.
Yeah. Eventually, you run into some sort of configuration.
Yeah, and it doesn't tell you. Just your database starts crashing, and you have no idea why. It just restarts again and again. Yeah. Okay, and so this.
They should get better at that.
They should tell you something, but anyway. So in the compose file, we're exposing port 8080 for the web server. And so that's exposed on localhost. So I just pull it up here. And so here is my Airflow interface. And I'll come back to this in a moment after talking some more. So core architecture, I've told you about some of this. We'll talk about some of the details. So the DAG files, again, provide a description of this graph of tasks. And then we have the backend database, which in our case is Postgres, web server. CLI can also communicate with the database, and I'll show you that in a moment. The CLI can send commands to the database, and then the scheduler and the executor will pick those up as well. Yes. Mm-hmm.
So is Airflow the wrapper or the innermost part?
In some sense, it's the wrapper around all of this stuff. Yeah, and so what are the components of Airflow? Well, you have core Python, because we're actually encoding these DAGs as Python objects. Flask is one of the primary components, and so the web server runs through Flask. And then an executor framework, which in this case happens to be Celery. Yeah, but it's kind of the wrapper around all of those things.
So that file, yes. The YAML file that you're showing.
So what I'm doing there is I'm running Airflow actually, how many times is it? I'm running 4 copies of Airflow, each providing a different service. So that does get a little complicated.
So each of those services so it has its own set of DAGs.
So that's a good question. They should all have the same set of DAGs. So you want to make sure they're pointed to the same DAG information, and then they sort of coordinate, communicate with each other to actually schedule tasks.
But that YAML file is not for Airflow, but
for Docker Compose.
Okay, which is just to set up sort of the equivalent of a machine to do this service, that service, and then they can communicate via the network.
Yeah, that's right. Yeah. And then this is a fancy demonstration, but actually, if you're using the basic local executor, then it's just 2 services. Just 2 services you need to stand up, basically. So you end up standing up your web server and your worker, and they can just work locally. But I guess this architecture is designed to scale. Again, it's just massive overkill for a laptop demonstration, but you can kind of see by looking at the architecture what happens when I want to scale out to a massive cluster of executors instead.
And in Airflow, the executor framework, is that configurable?
It's configurable, yeah. So you can execute on Mesos, on Dask, and Celery. And so Celery is the one I'm using with a Redis backend. But you can use Rabbit as well if you want to. So. Okay, so this is the executor I'm using here. And let me go back and just demonstrate real quick actually running something looks like. And so I have this really dumb example bash operator I'm going to show you. And so I can see the code here. And first of all, I define a DAG object, and then I define a series of tasks inside of that DAG object. So here's my DAG, and I have a cron expression that tells me when this is going to run. It's meant to run once a day. And I don't do that in this example, but you can template whatever queries or API calls you're running so that you're only processing data for those single days based on what argument is passed. And then what we end up doing, this loop builds out several different tasks and sets up some relationships between those. And so let's look at the visualization of these tasks. So let's go to the graph view. It's a little easier to see like this.
You make the text bigger.
Yes. How is that? Okay. Okay, so in this DAG, these 3 tasks at the top need to run, and then this one can run on its own, and then I'll run this last task. So to start it, I'll scale up again in just a moment. Oops.
Can you show the code for that again?
Yes.
So that is all.
So this is slightly confusing, but the 3 tasks in the middle are all created by this loop here.
Okay.
And then I have, okay, so run after loop here. It's a bash operator, and it's just going to run bash command echo 1. So it really doesn't do much of anything. And then run after loop set downstream. So what happens is I'm creating a downward arrow to run this last task.
And then the way that it creates that is by executing that script?
By scanning, basically. So it actually continuously scans that script, and each time it does, it checks dependencies.
Okay.
And it also generates this graph eventually, so it's available.
Does it its own sort of version control? So it scans it, sets a new version?
It does not. So that's something you have to be careful with. There are some proper ways to deploy DAGs so that you don't screw up your database, which I won't get into right now. But yeah, it just continuously scans and picks things up as it sees them. And so from a development standpoint, that's nice because I can spin this up as a kind of IDE for Airflow. So as I make code changes, I can see them actually show up in this interface, although it does take a couple minutes for them to propagate. But I don't want to do that with my production database because I'll get all kinds of weird tasks in there that I don't want to show up. Okay. So now I'm going to kick this off, and when I hit this on button, what's happening is the web server is writing to the database. And it's writing an entry in the database that says this DAG is now unpaused. And then the scheduler will look at that and say, okay, this is unpaused. That means that I can start scheduling these tasks. And it will actually, what it does is the scheduler also writes to the database. And it starts turning on those tasks, basically. Once they're on, the executor can start picking them up and executing them. So we'll see. It's probably already done now, actually. Yeah, it just finished everything. So these are very simple. They're just 1-second tasks, so it just kicks off, and it's done. And then what I want to show you is that we can add additional tasks and backfill. And so here's the thing that frequently comes up. And in my talk description, I talk about these ideas from DevOps and how you might apply them to data. One thing we sometimes want to do is essentially fork some location in our data pipeline. And so suppose that we have a version of a table, and we want to create a new version of that table. Maybe we want to add a column to the table, but we don't want to screw up anything downstream. So people are running SQL queries on the existing table. Let's create a new one. And so for that, let's go into the code here. I'm going to duplicate this last task, and then we'll edit it a bit. That came out weird. Yeah.
Sorry.
Yeah.
So a little bit more clear. So you're running these jobs to actually set up your database, like do your
Yes.
architecture?
Correct. So if these were real jobs, then instead of just running bash tasks
or SQL,
what you would do is you might make a call to Redshift. Say you make an API call to Redshift and tell Redshift to do something. So for example, you could have a task. Well, there's something called the sensor that can look for data to show up. And so I might have data that shows up in an S3 bucket. I can wait for that data to show up, and then that can trigger a task that then processes that somehow in Redshift.
But would you be managing like your database architecture? Like Redshift has this table. Would you manage like that table's definition in here, or do you manage that?
That one you would probably set up in Redshift itself.
Yeah,
so it's triggering the SQL query. categories, yeah. And so in practice, what we'll often do with like Databricks, for example, we define these Spark jobs in Databricks, and then we simply make API calls to kick them off at the right time once the data shows up or once another task completes.
Cool.
Yeah. Yes.
So those operators are the thing you're saving that also run this. Is that the operation or the result of the operation?
So the operator does something. Okay, let me talk about the architecture a little more, and then stop me if I don't answer your question talking about the architecture, and then we'll come back to this. Okay, so at the very most basic level, in terms of Airflow modularity, you have something called a hook. And a hook is a connection to some data source. At the most basic level, it could actually just be a connection to an API that you've defined. And there are some credentials stored there. Or it could be a connection to S3. And then operators, it's operators that actually do something. And so typically, an operator will involve one or more hooks. And so, for example, this is the S3 file transformation operator. And so this will pull some data from S3, do something to it, and then write it back out to S3. So in this case, I think we're doing the same thing on both sides of the transformation. But another operator could be grab data from the Google AdWords API and write it to an S3 bucket. Does that make sense? So operators basically execute something. They may move data around, or they may make an API call.
Are they the self-contained task, essentially?
In a sense, yeah.
So they
the
contain
operator's a genericized task.
the function to run, and what arguments that you're going to accept?
Exactly. And then you pass in those arguments. You might pass in the S3 bucket that you want to pull data from, or you might pass in the number of the job that you want to run on Databricks that you're triggering, yeah.
And do all of your inputs need to be serializable? Does it pass it between the network based on turning it into a string representation and then back into like all your arguments?
That's a good question. So the arguments in general, so your credential arguments are stored in the database itself.
Okay.
So there's a place where those are stored securely, encrypted. And then in general, the other arguments are all inside your DAG files. And so, for example, one of the operators we use at Overstock does stuff with Databricks, and so those DAG files then contain the numbers of those jobs that are passed in to the operator as arguments. Does that make any sense? Or?
Yeah, a little bit.
Okay.
I guess I'm thinking about this source S3, like one of the parameters, source S3 key. That's obviously a string.
Right.
But could you pass in a Python object?
Let's see. Let's see if I can.
I'm thinking the answer is no. I'm pretty sure celery.
I think it needs to be celery. Yeah.
It needs to at least be pickled.
Actually, yes, pickled. That's right. So you'd have to serialize in a pickle format or JSON or something like this. So.
Okay.
And then did that kind of answer your question, or? Yes.
Do you use TensorFlow at all?
Not much, but you do have DAGs and data that gets passed
Well,
around.
you have an execution graph that you build, and you take your operators, but your operator, and you pass tensors into your operators, and you get tensors out.
Okay.
So what I'm asking is you have this operator.
Yes.
You pass it things, and you get things back.
Okay.
What are the things you pass it, and what do you get back?
Okay. And hopefully this will be a satisfactory answer. So you mostly want to think of Airflow as more of a controller for other systems. It can move data around, but mostly what it's doing is telling other systems what to do. And so in that sense, it doesn't quite handle as much data so much as tell BigQuery or Teradata or Oracle to do something and move something. So that kind of makes sense. Or?
Yeah, well, I mean, so
okay.
There's some delayed execution.
Yes.
The scheduler decides how that's done.
Right.
And the DAG tells it what to do in what order.
Correct. Yeah.
But in the code, so specifically where you're setting this up.
Yeah.
Right. So is that when you were making the operator and you pass something back?
Right.
That could either be logically the type of operation, right? It's something like this is shorthand for I want you to do this particular.
Correct. That's right.
Or it could be this is the data from that And so it's that first one. It's,
Yes, yes.
So
And
it's not the data. It's the
correct. Yeah, you're not passing
operations.
data around. Any data movement that happens within Airflow itself will happen within a single operator. So there are cases where like my operator could actually pull data from Google AdWords and then write it out to S3. But then once that job shuts down, that state is lost. And so it's got to be saved out to some other system in order to stick around is the basic idea. If that makes sense. So it's mostly a controller. You want to think of it primarily as a controller for other systems.
Airflow, the only data that Airflow really theoretically should be passing around is net.
Right. Yeah. Except for these cases where I just want to quickly pull a report and then write it out somewhere else. Because it won't stick around outside of those systems that you're controlling, basically.
So, and I think that if I'm understanding this right, that operator that you're building when you do
Yes.
it in code
Right.
is essentially just like a lightweight object that says this is a node in my DAG.
Yeah, that's right. Yeah. Except that it might do something, but then once that task is done, that state is all lost. So it better be in some other
Unless you
system.
save it out.
Unless you save it out.
You're responsible for it. It handles none of your data.
That's right.
There's no data flow implicit in that DAG.
Yeah.
Just the operation.
That's right.
Yeah.
That's right.
Okay. And that's what I was
Okay.
confused because I was thinking of it. As
It's more like
TensorFlow,
naturally
which-
processing data, but it's just controlling mostly. Yeah. Okay, so actually I spun up the demo already, and so we have that up. And so the next piece I'm going to do here is just adding another operator, which is not interesting. I'm just going to run a stupid bash command that doesn't really do anything just to demonstrate. But of course, these could be interesting bash commands depending on what's installed on the machine that I'm controlling. So, all right, so I've duplicated this, and I'm going to call this, let's pretend that this is something interesting. Oops. So I'm going to match up names here so it's a little easier to read. So it doesn't really do anything, but there that is. And then if we look at the graph, where do I want to put this? You can actually configure this so that it will always show up top to bottom, but I didn't do that in my config. So what I'm going to do is pretend that this is sort of a fork down here at the bottom. And so I'm going to depend on the same two tasks that run this last depends on. So I kind of have another last endpoint for my DAG. So that means that I depend on run after loop and also run this. And so I'm going to add two edge statements to make that possible. So new table task. And you'll notice these other statements are downstream statements. I'm going to use an upstream statement instead, just convenient in this context. So let's see. Set upstream. So also run this. Run after loop. Okay, and then as soon as I save it, it should show up in the web interface, although it will take a second for it to actually process and convert it into a graph. So hopefully that's all correct. And let's see if the code looks right. Okay, so my code changes have shown up here. And so we'll give that a minute, and I'll just talk some more, but feel free to ask questions.
So I did a 5-minute tutorial online, or just looked at it.
Okay, and this is probably something that you did.
Well, I saw something like this, and I used the bit shift operators.
Okay, yes.
Otherwise you don't?
Yeah.
I'm just curious.
I'm just used to doing it this way, but that's right. There is a shorthand notation for set upstream and set downstream instead that you can use.
So there's no, they were just as well. You just
Yep,
that form.
exactly the same. Yeah, just depending on what you're used to. Yeah. So this is a warning because you can actually go home and do that compose file is online in the Git repo. You can spin this up, but be careful. So on the Apache dev list, there was recently someone posted and said that they had found a bunch of open Airflow web servers just sitting on the internet that people had not realized they should cut off. These types of dashboard environments should never be on the open internet. They're just not designed to be that secure. Like they're not hardened to be exposed to the outside world, even with authentication. And so if you do spin up something like this with real credentials, even for testing, make sure that it's like behind a VPN or that you have to port forward to get to it, port forward to the machine, or that you put it behind authenticated Nginx, something that's hardened and designed to be kind of in the war zone of the internet. So just quick warning, because it is so easy to set this up. Okay, so how many of you are, probably a lot of you are familiar with the microservice architecture. And the core idea here is that we want to break complex tasks into many different small components that run separately. Often these days, these tasks run, or these services run in containers, and they communicate through network calls, and each of these services will just kind of do one operation and then make another call, maybe to another service to do another operation. And there are a couple of concepts for how you can handle evolution of these services. There's this notion of continuous refactoring, and the question is, how do you handle that from a practical standpoint? So continuous refactoring means that we're changing not only the functionality of those services in their code, but we're changing how they talk to each other, and even the number of services we have. So we can change the API of the service. We might decide that we need to combine two services. Our site reliability engineers might tell us that something we have is not scaling, and that they think it will be more efficient if we just collapse two services together. Or they might tell us that two things should be split, because then one of those pieces can do double duty and receive calls from another service somewhere else. So in practice, how do you do this? Well, one way to do it is to kind of split out continuous deployment of bug fixes and minor changes to the service and refactorings. So refactorings in this case have to be carefully coordinated so that the other teams you're interacting with can know what changes to make to their calls to your service. Okay, so suppose that I'm trying to do things this way, but I don't communicate. And my Intrepid dev team decides that they want to move service 2 from accepting an XML payload to a JSON payload. Because why would we still want to use slow XML in 2018? Let's go to JSON. So they deploy their change, but they forget to tell this team that that change is coming. And so what happens is they deploy it, and then service 2.1 drops into that slot, replaces the in-place service, and everything upstream breaks, because now I can't accept XML like I used to be able to. And so one of the core ideas here is that we want to iterate rapidly, because that delivers value to the business. So we want to constantly be improving. That could be making our website more scalable. If you're Netflix, it can play more videos. Could be reducing latency. It could be adding new functionality. But there's always this risk of breaking things. And so how do we minimize the risk when we're making these API changes? Well, one thing we can do is use immutable services instead. And the idea here is that I never really replace anything, because all references to a service are an explicit version. And service 3 will always call service 2 and never service 2.1. So what happens after I deploy this? Well, I have a team and a process that monitors this service, and any team that's hitting this service will get a notice that the service has been deprecated, and they now need to redirect their API calls down here. So they need to do a redeploy. And if I'm really strict on this immutable approach, I do this for every release. Even a minor bug fix would merit a requirement to call the new service version. And that way I can never accidentally break something in production. And then, ideally, those changes propagate fairly quickly. These other teams make their changes, probably during the day. If it's not much of a change, then they can just redeploy something. So I'm calling the new version, and then this becomes deprecated. And eventually, I monitor. Once I have no traffic, I shut down the last copies of these services, and that's the in-production version now. And ideally, this is happening all the time. It might happen every day where you see new deployments like this. Okay, now how do we think about this for data? So if you've been in the data environment, you'll see these problems. In fact, your analysts, your data scientists, your engineers know where the bodies are buried. They know where the data problems are, but it can be very hard to get those fixes made, because when you change a table, you change a bunch of stuff downstream too. So there are a bunch of tables that rely on that table, just like a microservice architecture. You have these very complicated ETL data pipelines. One story from my passage over stock is that we had this data from a vendor, and that data had some fields that were not making their way into the database. In particular, there was a product description field that we wanted. And so we talked to the ETL teams, and they're like, well, it's going to take us a few months to make that change to the table, because...
That's fast.
Well, yes, that's true. But there were downstream somewhere where there was something like this. And so if you added a column, it was going to break the ETL processes. And even if you always have to worry about this unless you thoroughly check the code to make any table change, then stuff potentially could break. And so what we can do instead, potentially, especially with a system like Airflow, where we're unifying control of a number of different systems of data pipelines, we could simply create a new table. Let's go back here. We could simply create a new table. This is difficult with traditional on-prem infrastructure because you're always space constrained. These systems are very expensive, and you're probably operating right at the limit of what they can store. But if you're in the cloud, if you're in BigQuery or Redshift or Snowflake, this is no problem. You just add another table, and it costs you a small amount of money for a while. But then ideally, you do the same thing. You work your way downstream. You monitor who's hitting that table and which ETL processes in particular are hitting it. You notify those teams that they need to redirect to the new version. And then eventually, you get new tables deployed like this. I will say that, and this is a problem in every organization, as far as I can tell, garbage collection. You've got to do garbage collection. You can't just iterate like this all day long. And it's not really the cost so much. It's the cognitive burden of having so many tables floating around. Joe has lots of great stories about that. But anyway, you want iteration and cleanup, and then you can deliver features faster. So let's go back to our example, and I'll try to wrap up because I've been talking for a long time, I guess. But. All right, so let's look at our DAG and see if it's updated properly, and I certainly hope that it has. Okay, so we see new tasks here, and they have not been filled in because we'd have to re-kick this off to make that happen. And let's see if the DAG corresponds to what we expect. And it does. Okay, that's where we want it. So now what I'm going to do is rebuild. First of all, I'm going to fill in those two tasks. So I want to rebuild the data at those two nodes in my directed acyclic graph. And while we're at it, let's just go a little further back in history, and let's rebuild some additional history. So let's see. Okay, so what I'm going to do, this looks a little bit complicated, but really it's just that. We're running an Airflow command that does a backfill. It's going to do it on the example batch operator. It's going to start on this date and end on today's date. And it's roughly, what, 14 days or something like that. And I'm doing it inside a container. That's what those extra commands on the front are for. So let's kick that off. And then we'll actually see, this part will show up in the database, in the web interface almost immediately. So we can see that we have 16 new DAGs running, and we can see that we have 58 tasks in the recent tasks queue. And this gray color means that those have been moved to queued. And once they're in queued, my worker can start picking them up and executing them. And so we'll take a look at the details here. And so there's the history. You can see that these have completed, the dark green. The light green are running right now. And then the gray are in the queue and waiting to be executed. And so if we refresh once in a while, we'll see changes. And eventually it will fill all of those in. And so the idea is that we can use a system like this to do more rapid iteration, almost like you would with the microservice framework. It's not something we've deployed at Overstock, but I'm hoping that someday we can move in that direction so that data scientists and the business can get results faster by making these data improvements that are just kind of hanging around. So, and that's almost it. Let me just, I have homework, and so I'm going to post these slides online, so you can go through some of this homework and any of this that's interesting, you can play around with, you can spin up Airflow, you can create a DAG, all kinds of stuff. It should be fairly straightforward once you have some basic instructions. And that's all I've got.
Cool. Do we have any questions? Yes.
Were you able to get Fargate enabled on your personal account pretty easily?
Yes. So Fargate, I think, I'm trying to remember if I had to add myself to the beta or anything. That we're not on EKS yet, which is something we really want. But Fargate, I was able to run a container. I haven't had time to do a whole lot with it yet. But apparently, I just read that you can actually, from the command line, pass it a Docker Compose file. And it's supposed to just stand it up for you. So I'm hoping to do that maybe in the next couple of days.
Have you done anything with Fargate?
Yeah.
No, I just heard it's very difficult to get in.
That might be EKS, but yeah, because EKS we haven't been able to get into. There's Fargate ECS, and there's supposed to be Fargate EKS on Kubernetes as well, where you use Kubernetes files instead of CloudFormation templates. So.
Why EKS or ECS?
Mostly, so we're moving into Kubernetes on-premises as well, and so we want to just kind of standardize on Kubernetes pods, Kubernetes primitives, and also, how many people here have used ECS? It kind of has a certain reputation for being a little more difficult and less powerful than Kubernetes, but I can't speak to that in detail because I haven't spent a lot of
ceremony to it.
Yeah. I think it's probably one of those things where if you're already really good with CloudFormation templates, then it's actually easier. But if you're not, then you're doing something very domain specific instead of something more general with Kubernetes. Yeah. Yes.
So, are these operators like how heavy are they? Like
That's
if you wrote a for loop,
yeah,
right, and you said and the operator did the next thing each time.
Mm-hmm.
How portable would that be? Or does it keep? Is that the equivalent of doing like full, writing a function and then putting that inside the for loop in Python, or is that like spinning up a fresh instance of Python for each?
It does spin up fresh instances. Okay. So the thing to keep in mind is that Airflow is not intended really for tasks that take a second. It's intended for tasks that take minutes, really. And so, yeah, otherwise there would be very high overhead in all of this. And another tricky thing is that you need to be a little careful about how you define your DAGs. In particular, you'll often want to define operators right in the DAG file. So that's kind of the first stage of developing new connections. If you want to connect to an API that's not included in the core. The problem with that is that Airflow processes that file every time it scans. And so that could be high overhead if you're not careful about how you write that operator. If that makes any sense. So you don't want, and I need to dig into this more because I haven't encountered it myself, but there's some warnings about very heavy imports running every time you scan a DAG that can really bog down your schedule. So, yeah.
How does Airflow handle task failures?
It does have a retry mechanism, and then that's configurable, and so you can tell it that this task cannot be retried, and then it will just send you an email, or you can tell it to retry 5 times, and it will keep trying, and then after the 5th time, it will mark it as failed. So if you look at the task statuses the database can handle, there's no status, there's queued, there's running, there's successful, and there's in retry, and then there's failure. So in retry, I think it just tracks how many times it's tried so far, and then it continues to try.
Cool. If there's no more questions, let's thank Matt again. Can you pull up a Python terminal for me?
Yeah.
So the last thing that we do here at the Python Meetup is we have a raffle that we do for everyone here. So if you notice on your name badges, we have little numbers. Everybody look at your number now. I think we ended with 31. Is anybody bigger than 31?
32.
Got 32. Nice. So what we're going to do is we're going to open up our Python terminal. Low. Cool. Import random. Random.rand int. We're going to go 0 to 32. Cool. And we've got 2 things to give away tonight. We have this hands-on machine learning with scikit-learn and TensorFlow. It's a Riley book. Has anybody looked at this?
Yes, it's awesome.
Yeah? Awesome. And then we've got the illustrated guide to Python 3. I've heard really, really good things. Do you know?
Question, does random 0 to 23, 32, is that 0 inclusive?
Both our ends are inclusive
Do we
for
have
random.
0?
We do, because we are Pythonistas. And we started counting at 0.
We start everything at 0.
Yep.
That's awesome.
Cool. We'll let whoever gets first have their first dibs. Matt, do you want to do the honors of hitting enter?
Yes. Here we go.
Sorry.
Yep.
Asking you.
Yeah. 20.
I got this last time.
Nice. Well, come back down. Come back down. We need you to. We're gonna cue this back up. You can't win twice. I know you could come up twice.
Okay.
We got 10. And Ferris always likes to tell the story of his first book that he got, his first tech book. If this is not a book that you're interested in, feel free to hand it to somebody else. It might make their day and change the course of their life. History.
Yeah.
So that's all we have. Feel free to go out and mingle in our main area pretty much as long as you'd like. Use this as an opportunity to introduce yourself to other people. We're all awkward. Embrace the awkward. Just say, hey, how you doing?